Boom! All right, Will.
What is up, y'all?
Is there a y'all? Oh, I probably should have updated. I keep on forgetting to update the title of the chat. Let me go update the title for the chat. Uh, Dash transactions. A deep dive into the bits and bobs. There we go. Okay, let me check one more other thing real quick, and then I'll be right back.
Sure.
Oh. Let's see here. As I had feared, I need something soft but firm. Maybe some sort of stiff foam or something. Got a problem. Oh. I need to solve it. I've got my my door open, and I don't want it to close. I put a little rod in there, but the rod, of course, is making a dent in the door. So if I had a thick piece of foam, that'd be perfect. Anyway, all right. So transactions. Is that what we're on about?
Yes, sir.
Okay. Let me pull this window over here. And did you get a chance to play? Not did you get a chance. Did you play with the CLI tools at all?
I did not, but I did take a look at the code a little bit, and so I looked at dash phrase, I believe, and it looked like it was just a wrapper around the actual dash phrase, the repo.
Oh, all of the CLIs are independent. The reason for that being that often in a CLI you need dependencies that should not actually be present in the usage of the thing. So all of the CLIs are independent because they have debugging options, and they have, they're I hate it. I hate it when people publish a CLI with a package, and then you get this mountain of dependencies that are unrelated, and then they've got all these security vulnerabilities, and then they never get resolved, and you've got to go figure out, okay, does this package actually have a vulnerability, or is it literally because it uses mkdirp and it was never updated? So I like to keep all the CLI tools separate from the libraries themselves. That way the libraries are clean, and they only have the dependencies that they actually need, and there's no extraneous overhead of trying to figure out, when there's a security warning posted, does it actually apply, or is it just, something 10 layers down that isn't even used? So the library stuff, if it's in the dependency list, it's used. If it's in the CLI, then it may or may not actually be used in the library.
Yeah. So I mean that's the extent that I looked at it, but I feel like we went into a lot of implementation details, and if you could maybe summarize it for like 20 seconds to a minute or something, and then we can move on to transactions, that'd be awesome.
Yeah. All right. So the basis of all of the cryptocurrency stuff is the keys. So that's where we have dash keys. So let me get back to the actual dash keys.js. The keys consist of a random number if and only if that random number can be used to plot an XY point on on the elliptic curve. So any random number, 99.999, there's a few nines in there, percent of the time, any random number will be a valid private key. We add a little bit of metadata to that private key, such as a version number, a special byte number that's what causes it to always start with the letter X here. And there was something else, but there's just basically a few metadata, a few pieces of metadata, the version number and the
compression.
The recovery bit, the compression bit.
Oh, okay.
Yep. The recovery bit to identify, it is the compression bit, not the recovery bit. Sorry, the compression bit to identify that we are, like every other blockchain cryptocurrency, using the X value of the public key, because the private key has to be tied to the public key, and that recovery bit lets it know. And then there's a checksum at the end, and then the whole thing is taken together. And then that produces that, when run with you put it in base 58, which is a derivative of base X. That whole thing put together is the wallet import format, or the private key in base 58 check encoding with the extra metadata. The address, the payment address is similar. The payment address starts with a different magic byte, but it is still a magic byte that results in X being the first letter. And then it has the recovery bit for the Y value, which is part of the public key. The public key consists of the recovery bit for the Y value and then the 32 bytes of the X value, which makes it 33 bytes in total, and then it has the checksum at the end. So if I go to the glossary of terms here and we look at address, this is exactly what I just described. There's the version. Oh, sorry. No, this is not what I described, because I was talking about the public key before it gets hashed. I'm so sorry. It has the version, then the public key hash, then the checksum. The public key hash is derived by taking the SHA-sum of that recovery byte. It's a bit, but it's expressed as a byte, with the 32 bytes of the X value. That two pieces of information, there's a SHA-sum, and then there's a RIPE-MD 160 sum. That is the public key hash, which is only 20 bytes. It is not reversible to the public key, whereas the WIF is reversible 1-to-1 to the private key. So then let me go back down to the WIF real quick. So the WIF has the version byte that causes the X when base 58 encoded, the compression byte, which is just always the same because all cryptocurrencies used only the X value with the recovery bit, the checksum, and then encoded as base 58 check. So that is the whole of the key system. Private keys can be used to sign messages that include a pub key hash. The to address is the pub key hash, essentially, and the from address is actually the full private key. And we'll get into that when we get into transactions. I'll say no more. All of our documentation and examples come from two sets that are part of the original test fixtures, the zoomonic and the catmonic. The zoomonic is just zoo wrong, with lots of zoos and then wrong. That's the 12-word recovery phrase. The catmonic, it looks more random, and it starts with cat. So those are the two things. Any of the stuff in the documentation you find, if you're building your own implementation, if you want to check against it, those are the recovery phrases that generate the seeds, that generate the X keys, that generate the addresses that are used in all the documentation across this whole ecosystem. So the next bit would be dash phrase. What?
Sure. Sorry. Okay. So wallet input format is what? So I want to transfer.
Don't worry about it. It's a confusing name. Just don't even pay attention to the name. It's called wallet import format. That is a misnomer. It has nothing to do with what it is.
Okay. So
it is a private key.
Okay, so then the core of the explanation was that um, an address can be generated um, from your wallet, correct? That's
No,
like
I
the
wasn't talking anything about wallets. This was only about what a key is. A key has
okay.
nothing to do with a wallet. Uh,
Addresses. Can you sum that up in like a couple sentences or
an address is nothing more than taking random numbers. If the random numbers can generate an XY point, then the random number is qualified as a private key, and the XY point is qualified as a public key. You don't use the Y value because there's two Y values. If you put in an X on a curve, you get two Y's, and they're called even and odd. If the if you put in
oh,
an
because
X,
it goes sideways. It looks like somebody standing with a profile and they have a big old gut, and their gut is the elliptic curve, right? So if you draw it, it's from the top. You draw somebody's gut pointing to the left, right? And then the this is a really terrible example. You get what I'm saying, right?
yeah,
Can you
it
draw
is
it on a?
it's an elliptic. So if we look up
So I don't think
sec
most people have tried to
p
plot
two
an
fifty
elliptic curve.
six
So
256K1. If we just do an image search on this,
yeah,
so for any x value, pick any x value that doesn't go to infinity. So any x value that's over here, it might this might just go to infinity, and so that might not be valid or something. I don't remember exactly what the conditions are. But if you pick any x value, which can describe part of this curve, pick a point anywhere you want, there's always two possible y values. So if I pick, I can't pick an x over here, that would be invalid. And I can't pick an x way over here because eventually this just goes to infinity, and that would become invalid because we wouldn't have the bit capacity to hold the value. But the any x value in the allowable range of the curve is going to have 2 points on the curve, and one of them is called odd and the other one's called even. And so the recovery bit is an indicator, 2 for even and 3 for odd, and I don't remember whether they correspond to up or down or left or right or how it works.
okay.
But
Okay, this is a little more in depth, but so high level explanation. I'm a user. I'm not technical. I'm
then
coming
you don't need to
into
know any of this stuff. All you need to know
okay.
is
So
that
then
it's a random number. The random number can be used to generate a point, which is considered to be the public key. That you don't even need to know this as a user, but that the indicator of whether it is the even or odd value, along with the original x value, that is the public key. That is what's put together and hashed. That hash is the payment address. When a transaction is made, the payment address is the to value, the output, and the public key is the from value. So that is how it's structured, is that the public key is the from value, the public key is the to value. And the way that you could steal money is that you could just generate lots of keys, because 20 bytes is not really that much. An MD 160, you don't actually have to do the SHA. You could just do the MD 160, and then you can generate tons and tons of hashes, and you can create a collision at which you can create something that would collide, and you could steal the money that way. And that is a practical attack, and it has been done. But it's not worth it for Dash, because it's worth it for Bitcoin. It's not worth it for Dash, because it still takes thousands of dollars to produce a collision.
Okay. So
regular user doesn't need to know that either. But it's important that people in our community know that, because we need to eventually address this. Eventually, we need to have a bug fix for that. Other cryptocurrencies have done this. Dash has not yet. Many other currencies have not done it. But this is a known weakness that more people need to be aware of, and it needs to be addressed.
Okay. Okay, so then an address is, I want to get paid. Hey, AJ, here's my address. Can you pay me, however many dash for Taco Bell today, right? So
Indeed. Mini
okay,
dash for something as life changing as Taco Bell. That's not cheap.
yeah, at least 5 dash.
At
Um,
least.
can can you go into okay, before we jump into transactions, I guess maybe what a duff is, what a Satoshi is.
Okay. So there is this myth thing that the marketing bros like to say that Bitcoin is infinitely divisible. This is absolutely 100% and utterly false at the very core. I have no idea how anyone ever came up with such a notion. The Satoshi, I think the term duff and Satoshi are the same thing. I think that we need to not use the term duff. We can just pay
They're
our dues
they're
to
the same thing.
Bitcoin. Yeah.
So it's okay.
I think we can just pay our dues to Bitcoin and call it a Satoshi because there's just too much documentation and existing stuff out there. If we were to change our units, then we could call our units the duff. But as long as we're using the same units as Bitcoin, we just need to call it the Satoshi because there's too many places in the code that would have to be updated. And I wrote all these libraries or selected portions of them, rewrote some of them, wrote some of them from scratch. But I had some of these discussions, and the consensus, at least between Ryan and I and people he was getting input from, was that Satoshi is the term that we need to leave in the code. It doesn't make sense to change all the code to say duff. Just leave it at Satoshi. It's as far as this is already a very confusing industry, it's one thing that doesn't need to be more confusing than it has to be.
Okay. How many Satoshis are in one dash?
So this is really confusing because you expect it to be metric and it isn't. It is a 1 with 8 zeros, so a total of 9 numbers. So
Dash equals 1, 1, 2, 3, 4, 5, 6, 8
yes.
Satoshis.
Yes. So it's easy to talk about millidash, and here's the thing: we really need to just get away from anything that's below a millidash, because if you look at any currency, when you get down to millidash, in the worst case scenario where dash completely fails as a medium of exchange, and it grows in value to say, $1,000 or $2,000, even in that worst case scenario where dash is utterly failing, the millidash would only be worth 20 cents, and that's just so there's nothing you can buy for 20 cents other than perhaps a micropayment to view an article on a website, which I agree is a valid use case. But again, if dash balloons to $1,000 or $2,000, it's failed as a medium of exchange, and we have to go back to the drawing board, or we have to make really broad changes in the code in order to account for such a mishap.
So you mean if dash were to be 1,000 per dash?
Yeah, if it was
Like
$1,000, if it was
per dash.
$1,000 per dash, then dash would have just fallen to speculative investment and would be worthless as a medium of exchange. It would completely fail in its moniker of digital cash.
So I think I remember looking at the curve. I think it was on Coinbase, and
It did hit that.
Point.
Yeah, it hit that at one point for a week or two. It was during one of those balloon periods where investors had taken over and they were just scattershot investing and they were pumping and dumping dash. And so dash was a victim.
Ask that. What is the term pump and dump? What does that mean?
It's a form of money laundering.
Anybody do that?
It's a form of money laundering and kind of loan sharking. So pump and dump is when you use social media influence or current events to...
So like fear of missing out. Hey guys, Dash is X amount of dollars now. Everybody buy Dash. Something like that.
Yeah, so typically it's some influencer will buy a large sum of a cryptocurrency, and then they'll go out and they'll talk about how great it is. So, and then a lot of other influencers will get duped too. So Mr. Beast was in on one of these things with the NFTs, where
Oh,
there
I
was
know
somebody.
there's several influencers that have gotten caught in this, and they had no idea what they were doing.
Yeah, well, because they've just got some broha buddy who's like, "Oh man, this is going to be the next big thing." But the thing is,
Mm-hmm.
so that's the whole idea behind pump and dump is you buy something that's worthless, then you get a bunch of influencers involved and you make it as if something really big is going on, and then you sell off all of the worthless stuff that you had that's now become very valuable, and then everybody else who did what you said is left with the losses. And also you can look at what what Elon Musk did, where he kind of controls the value of Doge. So just last week he changed Twitter's logo to a Doge. That's a pump and dump, right? Because while he changes the logo to a Doge, everybody wants to go buy Doge. It's only 10 cents a coin or a tenth of a penny a coin. I don't know what it is, but it's, a ridiculously small amount. And then he's able to dump his Doge and,
Wasn't that a joke coin anyway?
It is, and that's kind of why he probably isn't in as much trouble as he otherwise would be, is because it's markedly a joke.
People are trying to sue him because supposedly they're acting like her. I think that was the basis for one lawsuit, right?
Well, they're right, and he's right. They're right. He is doing a pump and dump. He is manipulating something, treating it as if it's private security. But he's also right in that it's literally a joke, and he's just kind of making fun of how dumb people will behave. But then a lot of the people that are getting rich off of it, they're not that dumb because they understand the way that the pump and dump scheme works, and so when they see something's happening, they just play along because it's like, well, somebody's going to get rich off of this. Might as well be me too. So, yeah, a lot of the value around Dash has unfortunately been... the reason that Dash is so volatile is we don't presently have an economy. What we have instead is we have a lot of speculative investors and pump and dumpers and money launderers, and they need to diversify in order to justify what they're doing. Because if they just did it in one particular coin, like what Elon Musk does, then they would get caught, except that, he doesn't get caught because he's doing it as a joke with a joke coin. But, that, and so they diversify into lots of other things, and that's what pumps up the value of the other things that aren't related at all. So Dash doesn't participate in money laundering. Dash doesn't participate in pump and dump. Dash as a community doesn't participate in any of this scammy nonsense. However, Dash does get the runoff of it. And so it benefits us without us intending for it to happen or doing anything nefarious to cause it.
Okay. Okay, I guess we can do transactions now. What's a good high-level explanation of what a transaction is?
It's an email. It's an email on the blockchain. It's an email with a value prescribed to it. So the email has to and it has from. And every from needs to sign every to as well as every other from. Basically, there's a few different types of a transaction. There's a raw transaction. There is a ready to sign transaction. And then there is the fully signed transaction. And let me see if I can actually bring this up to show how this works. I think I've got it in this issue called the How to Calculate a Signature. Because this is really unintuitive. We'll keep it high level for now. We'll keep it high level. It's just there's three versions of a transaction. It's the bytes packed in a different way, and it's basic.
What repo is this?
This is -TX.
-X. Okay.
And there's an issue called How to Calculate a Signature. This is also referenced in the README. And there are examples. I haven't pulled the CLI for this out yet. I will. But you can see here, these are the literal bytes of a transaction. And it is a hodgepodge of different binary standards and schemes. And this is the same scheme that all of the Bitcoin-based cryptocurrencies use for payment transactions. There is not anything that Dash does, as far as I'm aware. There's nothing here that's unique to Dash. There's literally nothing. I don't think that there's... I think that we have a different version number not because of the way that our payments work, but because it's an advertisement that the version number of the network has incremented. So there have been a few changes, basically new message types that didn't exist before. And I believe...
So this is a block version, right?
This is what?
This is a block version?
This is a network version. I think that maybe that's synonymous with block version. I'm not really sure.
So
let's say yes. I think probably.
So a block is one or more transactions prefaced by a block header. A block header is 80-byte header prefacing the rest of the block. And then there's block versions, which is a field that indicates what validation rules to use. Does that sound...
No, that doesn't sound right. I mean, I could be wrong. I don't remember the exact number of bytes here, but this is not a block. Transactions go inside of a block. So the M&Os
go inside a block. Okay.
will aggregate these and layer them and then sign them.
And what are M&Os? Master nodes?
The master nodes. Well, yeah, I technically the M&O is actually the owner, but I just hate the term master node. It sounds so technical and also ominous.
Yeah.
So because they're actually the service nodes. They are not master nodes. They're slave nodes, if you will.
So master nodes will sign a transaction?
They will aggregate the transactions and sign the block. I'm not sure what the process for that is. I have not gone into that. I have not been working on block signing stuff. Everything I've been working on is from the user perspective, things that you'd want in a wallet. I have not worked on hardly anything other than the voting process that you would want, and even that could be done through a wallet, and probably should be done through a wallet. But I haven't worked on the other stuff.
Okay, so I have master nodes will aggregate the transaction, and they will also sign a block.
Yeah, that's the way that I believe that it happens. They select which transactions will go in. And in Bitcoin, this is where this is quite different. In Bitcoin, it's based on the fee. In Dash, it's based on nothing.
Sorry, what's the way they sign it? Or sorry,
so in Bitcoin, you have to pay a very large fee in order to do a transaction. Dash doesn't really have a mechanism that's used in practice. In theory, it would be selected by the value of the fee, but in practice, it isn't. In practice, all transactions are accepted by masternodes. And if that were to not be the case, we would need to make a change to the protocol because, again, it would fail as a usable exchange of value. Because if the cost of exchanging value starts to encroach on the value, then you are you've got the same problem that you have with Visa, which is the problem that Bitcoin has times 10. Well, I guess it depends on what. Yeah. You couldn't buy a burger with Bitcoin. You can buy a burger with Dash. The fees in Dash round down because they are basically everything after the first 3 digits you can just ignore because it's worthless. So 1.001 Dash, that 0.001 is pretty much worthless. And everything below it is definitely worthless.
Okay. So transactions are part of blocks, right?
Yeah, so blocks have various types of messages, and payment transactions are one type of message. But people put in their children's birthdays.
So blocks have various types of messages, or would it be transactions?
I would call it messages, because a transaction, to me, I don't know what the literal definition is, so I may be using it wrong, but to me, a transaction is 2 parties exchanging value.
Mm-hmm.
You could also say a transaction is any action, period. And you could argue that the masternodes are parties to the transaction. It's not peer-to-peer. It's you go through the masternode owners to get your transactions approved. So, you could argue that any message is a transaction because every message does cost an insignificant amount of dust. Dust is a term for useless money. So traditionally dust is 2,000 satoshis or lower. That would be 0.00002. And transactions are well below the dust value. So, or messages. But so it costs money to send a message, but a message does not have to be, a message could be a vote, a message could be a payment, a message could be it could literally just be text. You can just put text into the blockchain.
Isn't this so I saw something they want to host files on Dash?
No, this has nothing to do with that. This is not related at all to that. That's a completely separate protocol. It's using the same what's it called? It's using the same distributed hash table to be able to find nodes on the network, but it's unrelated at all to any of this. Other than that, there is, if you wanted to use that service, you would need to post a payment to the Dash blockchain, I think. I'm pretty sure it goes to the blockchain. It goes to the network. The payment goes to the network.
Okay.
But that, yeah, it's not related to this. It's a different set of services, different protocols. There's going to be some shared things, such as the way that using the same curve for the signing and verification, using the same private key size, using the same address mechanism for payment addresses. Xprivs or Xpubs, as contacts. So there's a lot of the same stuff will be embedded in those messages, but they are not. They're dissimilar systems. Because if you were to try to store files in the blockchain, or it's untenable. It's a very bad format,
So what is the you said somebody can store the birth date or something?
Yeah. Yeah, it's vanity. It's complete vanity. There's no utility to it. It's just to be able to say, hey, it's like getting a vanity license plate.
So
Or
are they, they're just storing text content, just random text content? Oh, I just want to store this on the blockchain.
yeah, so the the miners and masternodes, etc., run what is considered to be a virtual machine. So it has its own set of assembly instructions,
Oh,
and
is that
it's
pub key scripts?
yeah. So the pub key script that's in here. So that's part of this, but the scripts are assembly code for an imaginary CPU, and the interpreter for that imaginary CPU is embedded in the master nodes and the miners and such. And this is how, so rather than a data format, when I look at this, I think of it as a data format, because to me that's what it is. I'm saying it's to addresses and from addresses. But the way that the people who designed this looked at it was as a programming language. And so to them, whereas I'm saying this is a to instruction and this is a signature, and I would say that the key for this is verify signature and the value for it is the signature. They would say that this is a virtual machine that uses assembly instructions for a stack-based virtual machine. And I think treating it that way is ludicrous, but that is how they originally envisioned it, and that is what Ethereum has taken to the extreme.
Okay. So it's a
So there is a no-op. There is a no-op. And so what you can do is you can create a message, put some text, and then use the no-op assembly instruction. I think it's actually just called op return. I could go back maybe to this one. Let's see. Yeah, so op dupe, op hash, op verify, op check. So there's a whole bunch of these. Very few of them are useful, and for what digital cash would be. So you can pretty much treat it as key value pairs.
These are the core of what its validation rules, right? So
yeah,
it's how does that relate to consensus?
I don't know, because I have not done anything on the server side. I'm working completely client side.
So if I may, I think all nodes are in consensus when they've all validated every transaction, something along those lines, and then the rules are the pub key scripts, and when all those validation rules are passed, then it's a valid transaction or a valid block or something like that. I think that's how it goes, because I actually looked this up a long time ago, but I probably know less about it than both. Yeah. Anyways,
I don't know. That is something that I don't think that I'm ever going to get into, because there's so many other useful things that could really solve the problem of digital cash, that I kind of look at it like a Rube Goldberg machine. And, Ryan says, well, it's only a Rube Goldberg machine if you have a better alternative. I don't think that's entirely true. I think it's kind of, if a tree falls in the forest and nobody heard it, it still fell. But But from the perspective of, it might be one of the worst possible ways to do it, but if it's one of the only ways to do it right now, I agree. Fine, let it be. Let's fix critical problems, but let's just move on, and one day we could, make it better. But the stuff that's going to have impact for people is going to be the stuff that is user facing, the ability to send money, and the getting back on track with the idea of, I hate to say privacy, but there's a lot of efficiencies that we can get to if we get rid of the idea that every transaction should be fingerprinted and that this is somehow a good idea. If we just abandon that notion and say, why don't we just opt for, we don't fingerprint by default, there's a whole lot of stuff that gets way simpler. And also, this is something I hope to see and I would be willing to be a part of, is we could get this whole database out of Berkeley DB and into something like SQLite or Postgres. And, there's a blog article called Doing 4 Million Transactions Per Second in SQLite. And I think that would be something to look at, because they're talking about how basically on relatively inexpensive cloud services using single servers, they got 4 million transactions per second in SQLite. They did put in a couple custom modifications, and there's a little bit of an issue of flushing the data. They wait longer to flush the data and stuff like that. But when you consider something like a blockchain where you have lots of nodes that are holding the same data anyway, that's completely not a problem. But I think if we got this into a real database and then we started dropping the spent money so that the size doesn't grow, and then if we just started applying a non-transaction fee, we need to get rid of the transaction fee and apply a non-transaction fee, and then we could just drop all the stuff that's the op returns and stuff with people's birthdays, which I know would really upset a lot of people, but it also would make it simpler, more secure, and less fingerprinty.
Yeah, so Berkeley DB is a key value store.
Yes.
So if they're using it as a relational database, which is a common mistake that's made, I can see moving to a different DB.
It's more that Berkeley DB is not. You cannot get good drivers for Berkeley DB. There are very few options. It's not implemented very well in modern languages. All modern languages have implemented SQLite. Well, JavaScript hasn't, but most modern languages have implemented SQL. Well, I guess implement is a strong word. Never mind. They have connectors for it. So okay, I take it back. SQLite, I don't actually believe has been implemented in modern languages. Sorry, scrub that entirely. But it's very easy to get adapters for SQLite in modern languages, and there are kind of a level of compatibility that you can get with SQLite that you can't. Berkeley DB is not well supported in the modern ecosystem of programming languages. That can be easily stated.
So what else is within a transaction?
Okay, so we go back to transactions here. So like I said, it is inputs and outputs. It's to and from. So the inputs are the froms and the outputs are the tos. And let me go back to the one that broke this down a little further.
Outputs. And then the outputs are twos. Okay.
So you can, well, there is a -tx inspect tool that comes with this that will go into the CLI when I pull that out. But you can take a transaction, you can take the hex of it, and it can be broken down. The first thing that it's going to be is what is this? A 32-bit int that is the version number, and this is big Endian encoded. So the most significant byte comes first.
Yeah.
Or wait, no, the least significant byte comes first. Which is weird because it's called big. No, this is little Endian. Sorry, I get my Indians confused. In one of the notes I had on this, I put by whether it was LE or or BE. Okay, here we go. Little Indian. Little Indian, right?
Mm.
So these are in CPU order rather than in network order. CPU order is Little Indian, network order is Big Indian, and I think that has something to do with the first in, last out, something like that. That I think it harkens back to the buffers that they used on early network cards. But
So you often have to deal with that with protocols because they assume that machines that they were communicating with had different bit orders, but now everybody's basically big or little Indian, and we're converting to big Indian where we have to.
well, almost everything is Big Indian when you view it as a user, right? If you do any sort of conversion in JavaScript or Ruby or any language where there's interpreter, it will show it to you in Big Indian format, and that makes more sense because then sentences are actually in order, strings are in order, numbers are in order, as we read from left to right. So as far as network order goes, that makes a heck of a lot of sense over Little Indian because we'd have to read everything backwards, like this, where this is actually the least significant byte, but it appears on the left rather than on the right.
Okay.
Now, this is where things get weird. Things are weird all throughout here. So that's a little weird because do you really think that you're going to need 4 billion versions? The good news is that we could bump to a version 4 and the version 4 could declare that the rest of these bytes get used for something else. I don't know what. But the bad news is that, so this represents something that's always going to be a low value. You know, what are we going to get to 15? 1,000? But we've got a full int here. What's really weird is that the number of inputs is a var int. And it is I believe that it is an ASN1 style var int. Are you familiar with that?
No.
So it goes all the way up to, I think it's 252? So a single byte can hold a value up to 252, I think. I might be off by 1. But once you reach 250, let's say it's 252, I could be wrong, it could be off by 1. But once you reach 252, then it becomes 2 bytes. And the first byte tells you how many more bytes there are. So in that case, and the way that it works is that 253 means 1 more byte, and then 254 means 2 more bytes, and then 255 means 3 more bytes. And I think that it may go higher than that. I think it might go... No, I think it's 2 more bytes, 1 more byte, 2 more bytes, 4 more bytes, 8 more bytes. That's the way it scales. So that is a var int, and I think I've got that documented in here. Let's see, var int. Let's see if I have an explanation of var int in here. Okay. That is something that we should have documentation for, but it's easy. It's probably easiest if we just look at the code. But for now, let's just say that a var int is, it follows a sequence by which, as the number needs more bytes to express itself, the first number goes above 250, and then that number is encoded in it how many more bytes there are. So if I want to express 255, that's actually 2 bytes, not 1. And if I want to express 16,535 or whatever it is, then that would be 3 bytes, not 2. But then if I want to do the next one up, that would be 5 bytes, not 4. So for small numbers, which is what you normally have, you only use 1 byte. But for large numbers, you use 1 extra byte than what you would have used. Potentially.
So it looks like it's a serialization format.
Yeah, it's called compressed ints or var ints.
Hmm.
But this is weird because there's lots of other things in here that aren't compressed bytes. They're not var ints. Then the next thing is going to be the transaction ID on the blockchain. So this doesn't say which block it's in, but it says which transaction it is. And it's going to be the transaction in which this input received the coin that is being spent. So everybody talks about the, coin, but the coin is actually a real thing. The coin is the combination of a payment address, a transaction ID, and an index in that transaction. That references the coin, and the coin is the value that's found if you follow that chain. So look for the transaction, look for the address, look for the index that matches, and look for the value that was assigned. And this is a little bit out of order in terms of logically how we would think about it, the way that it's organized in bytes, because where that order is found is actually in the output, but it's in a previous output. So the input references a prior output, which output placed a value to a payment address at a particular index. Because you could actually put out multiple payments to the same address at different indexes. So you could say, I'm going to pay you 5 Satoshi, and I'm also going to pay you 10 Satoshi. And that would not be a transaction of 15 Satoshi. That would be a transaction of 5 and 10 Satoshi. Of course, those numbers are so small that they're incalculable, but just to avoid saying the word cent or dollar. Does that make sense?
I mean, it's a lot of detail, but yeah. So what else is? So we have inputs, outputs.
Yeah, outputs are coins. Outputs are coins. Yeah. And there's 2 types of coins. There's spent coins and unspent coins.
UTXOs.
Yeah, unspent transaction outputs are coins that can be used.
And those are the only kinds that can be.
Yeah, I mean it's kind of yeah, exactly. It's kind of a case of somebody got a little overzealous with giving things interesting names that sound cool in a white paper.
Okay.
Because basically, money you didn't spend yet. That's what a coin is. Coins you have are things you didn't spend yet. The end. It is no more complex than that. Well, other than that it is an addressing scheme. Just like HD path is an addressing scheme to an address, the coin is an addressing scheme to where the money was loaded.
Okay. My wife is texting me about some Asian place that just opened down the street.
That's good.
There, so, yeah. Hot pot is what they call it. I don't know if you've ever had that. It looks good.
I have been to a hot pot generically. I have probably not been to that hot pot.
Yeah. Okay, so we have transactions. They have inputs. They have outputs. So let's say, can you walk me through, let's say, like a super high level of, I pay you 5 Dash. Can you kind of go through and show me how those transactions might be formed, how it might relate to everything else?
Yeah. So that's all right here.
Cool.
So, in this one, I was actually showing the, let's see, let me get back to where I was showing, here we are. Okay. So there's a number of from addresses, and then there's a number of to addresses. So inputs are froms, outputs are tos. And so if I want to send you 5 dash, I got that 5 dash from somewhere. So I have to identify where that 5 dash came from. And so I have to dig up an old transaction, and then I have to say this old transaction. So this whole thing is a transaction. So it's a little bit recursive because a transaction is defined by a prior transaction. So there is, at some point a Genesis block at which there were no
first one. Yeah.
There were no inputs and there were only outputs. And then there are also reward blocks that I think work in the same way, where there's no inputs, there's only outputs. So every time a coin is mined, every time masternodes get their reward, every time the super block contributes dash to the network, meaning for proposals and stuff like that, I believe that those are blocks that have only outputs but don't have any inputs. And that is allowed because the masternode owners run the same software, and that software dictates the rules, and they are able to follow the rules for a transaction that only has outputs and no inputs. Or something similar to that. So anyway, every time, so with the exclusion of the special blocks that are just described, every output has to have a prior, or every input has to have a prior output. So what I would do is my software would go find the address and look for all the transactions in which that address has appeared, which should be exactly one, unless it's Coinbase or other malicious software.
Can we do it where I'm paying you, just for this example?
Sure. You're paying me 5 dash. Okay. So your software is going to look up your address either in a local cache of the blockchain or using DashSite or whatever mechanism that it has. There doesn't have to be any prescribed mechanism. It just has to happen. So it has to look up all transactions in which that address was used, in which the transaction has not been referenced as spent. And it may actually be easier to first... Let's talk about outputs first, because then outputs are a little bit easier to reason about because they don't require recursion. They don't require you to have some place that it came from in order to define it. It's not what's the word? It's not a tautological definition. So with the output, so what you would do is you would say, I'm going to take AJ's address that starts with an X for dash. I'm going to decode that, and I'm going to get the pub key hash. And so I'm going to let's see here. Whoops. Okay, where was that? Sorry, I got distracted for a second. A message popped up that took brain cycles, and I processed it, and now I got off track.
Okay, so I'm paying you. I take your address.
So you're gonna... Yeah, so I can just generate an address out of thin air. This never has to have been used before. I can literally just roll the dice, and if I can plug the numbers that I get into the elliptic curve and get a valid public key, that's great. And I take that and I hash it down to just 20 bytes long. And that's these 20 bytes right here. So this 14 is hexadecimal for 20. So it's saying that the length of the address is 20 bytes. So this 0x14 is decimal 20. This is the RIPE MD 160 sum of the SHA-256 sum of the concatenated Y recovery bit with the 32 X bytes, which is the public key. So that's where this comes from. And this is decoded from the address that I give you. So I don't even give you my public key. I give you that X value that has the checksum bits on the end and this information in the middle. Your software decodes it, and then your software is going to put in how much of so all money is spent. There is no way to not spend the coin. Every coin that goes into a transaction will be spent entirely. And this is where, the fingerprinting by default problem lies, and where the hold on, where the change issue lies. Because you would think that what you would do is you would have an output to pay the network fee. But I guess because they were theorizing that one day Satoshis were going to be worth $1 million each or something like that, that they wanted the fee to cost less. So you pay per byte as the fee in the Bitcoin tradition. And I think we could very easily ditch that tradition. But in the Bitcoin tradition, you pay a fee per byte. And so the fee in itself is not an output. The problem with this, of course, is that you have to have an output back to yourself that describes the change. And so you have net zero. You still have to put the bytes there. And now you have to fingerprint yourself. But everything that goes into a transaction is completely spent. And if you do not specify where it goes, then it goes to the network. The default behavior for any unspecified value is it goes to the network. So you put the coin, the output, because it's not randomized and it's focused on making sure that all transactions are fingerprinted. The first input is always who you're sending the money to, and the second input is always the money that goes back to yourself. And I don't know why this is a 64-bit integer, because it's literally not possible to. There's not that many Satoshis.
So,
but there's a 64-bit integer describing what the value is in Satoshis.
So I'm paying you. 1, you come up with an address. 2, I take that address, it decodes it, I get the pub key hash. 3, the output contains 2 things, which is 1, who I'm sending it to, and the money that goes back to myself.
So it actually is defining several things, but these are the important bits. Who's it to? What's the amount? The other bits are the lock script size. So, there's sizes. So there's the size. This doesn't have a size. It's always 64 bits for whatever reason, even though it's not possible to spend that much. Then there is
that the Coinbase transaction? Or
I don't know, but I have seen that term. I thought Coinbase was something like the block. The technical term Coinbase, not the company Coinbase, I think refers to the super block type of thing.
Okay.
Like the Genesis block, the base of the coin, where the coin came from at the very beginning. But this is how many base units to send. And this is the lock script size. This is the lock script. Well, I guess this is the script size. We're using a lock script, and this is a lock script. So this is 2 assembly instructions. And it's the instructions for what has to happen in order to spend this. And so this basically identifies it as, in order to spend this, you have to be able to verify the signature. And then these instructions go along with these instructions, but because it's stack-based, part of the instructions come before the address, and part of the instructions come after the address. But in whole, these instructions say that in order to spend whatever went here, it has to verify a signature.
So this is the pubkey script.
Yes. Pay to pubkey script. Wait, no, sorry. The script to pay to public key, because there is a pay to pub key script, which is an entirely separate thing. This is the script to pay to a public key.
script to pay to a public key.
It is.
And
I have not implemented the other bit, but it is also possible to pay to a script. That's a smart contract.
Okay.
Essentially. And
I'll
you
just
can
go
also
with-
specify rules that say that there have to be more than one signature in order to spend something.
So this is a validation rule?
Yeah, it's a validation for it is an unlock. Okay, sorry. This is a locking rule. And the locking rule describes how the funds can be unlocked. It is possible to construct something that does not require an unlocking rule, which meant that if you were to publish it, anyone would be able to claim it. But you probably wouldn't want to do that in practice.
So is there usually a different type of... Is there usually only one type of script when paying? So like this particular situation,
In practice,
I'm paying to you.
In practice, you're going to have two. You're going to have who you're paying, and then you're going to have yourself.
Okay. And then, but I mean, the script, as far as like scripts go, is it usually just this lock script that's going to be attached?
Yes, that is almost always what it is. But there is, like I said, there's the no-op script, and the no-op script will allow you to just put random garbage, whatever you want.
Okay. Okay, so I described a script to pay to a public key just for academia. Can you tell me what the other thing was? You said... Do you remember what you said?
There is a pay to script. So there's a way to say it's basically a smart contract. So you don't pay to an address, a pub key hash. You instead pay to a script that has some additional rules. So when the smart contract conditions are met, the money is released.
Okay.
Now, the extent of that smart contract, I don't know, but that's kind of the basis of Ethereum. Ethereum took that idea and then just, ran right off the cliff with it.
Okay, I'll just put bonus trivia. Okay, so we know... Oh, okay, are you done describing the outputs?
Yeah. In practice, this is all we have. Now, you can have multiple outputs. So one thing that's nice...
To different addresses, or...?
Yeah. So you don't have to only have two. Typically speaking, you have to have at least one. And I think that is defined at the software level of the server implementation. You shouldn't have to. You should be able to just donate to the network, and I want to file a bug over that because, again, fingerprints first. But you have to have at least one output in the current implementation. I consider that to be a bug.
So what you're describing is I have 10 dash. I want to pay you 5 dash, but I have to make two outputs, one being a change address.
You actually have to make three outputs, but one is implicit. So one is so inputs minus outputs is the fee.
Okay, so let's see. So outputs will be y paid AJ, change address, and then, sorry, what was that last part?
Inputs, sum of input values minus sum of output values is the network fee.
So you have to have three outputs.
There are two outputs that go in the output section. The third output is implicit. The network fee is implicit.
Gotcha.
Yes.
Okay.
So there is nothing here that describes the network fee. There is no indicator of network fee. Network fee
a ghost
is
output.
Yeah. Good way to say it. It is the sum of the inputs minus the sum of the outputs. So if you have a nice round 10 dash and you want to make a nice fingerprint on it so it's easy to track and trace, all you have to do is send someone else a nice 5 dash, and then you're going to get back a random number. What's up, sweetie?
It's in the field. I tried to get her not to come over here.
Oh, it's fine. It's fine. You're going to have to listen to what Miss Teresa says, okay?
Daddy's working too hard.
If I have to close the door, I will, but it's a nice day, so.
Yeah. I tried to keep her from coming over here. No, not you know. Here, get some bubbles.
All right.
Okay. I did not know that about the ghost output, so that's interesting. Okay. Interesting. Can we break for like 2 minutes?
Yeah.
I'll be right back.
Okay. All right, and I'm back.
Good day.
Are you back?
I am back.
Okay, cool. I will take these down. All right. So, what I was saying is, if you have 10 dash and you send me 5 dash, then you're going to send yourself back 4.9999987. I forget what the number is. But yeah, you're going to send yourself back that much. And then that's going to mix in with your other dash. And then as you create transactions, there's a steady stream showing every single time that you've made a transaction.
What is proof of work?
We don't really have to worry about that much in Dash. That's being phased out, and there is a retirement plan for it. But proof of work is the idea that You want to produce as much greenhouse gases as possible, and however many greenhouse gases you have produced, you win money for it. So you basically you burn CO you burn coal in the form of electricity,
So
and then you get rewarded for the amount of coal that you've burned. But to say it, yeah, it's mining. It's you're doing terahashes. You're playing a guessing game. So basically, there's in the block that I believe, I could be wrong about this, but I believe the block is counting down to 0, and the difficulty of the block is how many things you have to do to match. So every block has a number, and I think it's counting down from FF whatever. There's a difficulty algorithm that is how many digits you have to match in order to be considered complete, and then the previous block, a hash value in or of the previous block, I'm not sure which, is used with the current block. I think it's the block height. I'm not sure. I have not looked at this code. Could be getting the values wrong, but this is the essence. Something about the previous block, that way it's unknowable, because you can never know what hash. You can never guess a hash in the future, because you can never know what hash of the hashes that will match will be the hash that's chosen. So every next hash is dependent upon the previous hash, and you're playing a guessing game where you're just running hashes and then basically incrementing a number. And in the Bitcoin tradition, the groups of miners are basically distributing out numbers. Okay, you start with 2 billion. You start with 4 billion. You start with 8 billion. Or 6 billion. You start with 8 billion, and so on. And every computer in the group is trying to hash its way up to the number that it was assigned. And if it finds that its incrementer, along with the previous block hash, matches the next target hash, then that value is submitted for validation. And that is what mining is. So as more miners join the pool, the algorithm selects based on the time between blocks. And so as more miners join the pool, then the complexity of the problem, how many bits need to match for the solution to be considered complete, gets incremented, so that in any block, the challenge might be twice as hard or half as hard as the previous block. So this is why there's an arms race with it, but again, we don't really need to go into that because this is not important in Dash. It's vestigial in Dash. It's something that the sooner that it can get annexed, the better. The only thing that it's just right now, it's a waste of otherwise good utility for the network. But like I said, it's phasing out. It will go away. Probably not as quickly as we would like.
Okay. So I guess back to transactions. What more is there?
So there's lock time. So this can be part of staking. Is a much broader term than what most people imagine it to be.
Staking?
Staking is when you put money in a place for a specific amount of time.
Okay.
And if I'm not mistaken, lock time is given in blocks, because the blockchain doesn't know about the time necessarily. None of these values in here are in regards to time. There might be a date stamp in the actual block itself. I imagine that there probably is. But I think, I could be wrong, I think lock time is in regards to blocks. We should probably look that up so we don't lead people astray. but you can guesstimate the amount of time based on the number of blocks because you know about how long algorithmically on average it's going to tend towards the target, because if it overshoots, it's going to undershoot the next one, and so on and so forth. So it's going to average out. But let's see if this is given in actual time. The earliest time or block. So that is actually not helpful. I think that, what does locked mean? First moments. Okay, before that block is reached. That's what I thought. So I don't know if this is accurate, but assuming this forum post is accurate and my assumption is accurate, then what we're saying is you can put in the lock time some future block that you can estimate. In the case of Dash, you can estimate that block to be 2.5 minutes away. So if you want to say this money can't be spent for 6 months, you calculate the number of 2.5 minutes in 6 months, you take the current block height, and then you add that number to the current block height. And that would be your lock time. Or I could be wrong, and it could be an increment from the current block. I'm not sure which it's supposed to specify.
It runs the unlock script at that time.
No, it is not allowed to run any unlock script before that time.
What I mean is after that time. So after that time, it runs the unlock script.
No.
No?
Anybody can run the unlock script at any time, or rather they can submit a message with an unlock script at any time. It will not be honored unless it's at this time.
Gotcha.
So it will not go back to run an unlock script. It will simply reject it.
So what I mean is that script is what will release the funds if that time matches. Is that?
No. So in the future, in a different transaction, I would create an output where that, no, I would create an input, sorry, because as you'll notice, outputs and inputs are unrelated. They don't say anything about each other, other than that the output that's the last one is always the change in the current implementation, as far as I understand it, which I hope I'm wrong. I hope somebody, calls me out and says, no, it's just that you're using bad software that does it the wrong way. And I would agree. That's terrible. But the outputs and the inputs are not related. The sum of the inputs must be greater than the sum of the outputs to account for the network fee. But there is no script here that will unlock anything except for the inputs. The inputs are unlocking some other previous output.
So outputs don't have lock scripts?
Outputs have lock scripts. The input has to match the rules of the output. These are nuanced differences. The wording is slightly different between what I was saying and what you were saying. But it is different. You do not unlock. The conditions for unlocking are part of the outputs and the lock time. So what it's saying is that if there is a lock time specified, none of these conditions can be met until this time has been reached. So it means you cannot publish a transaction that would satisfy these conditions before this block, whatever this block is, or if it's an increment, whatever the increment is. But I think it's a block. That seems a little, I guess.
So when does the lock script run in the output, or does that?
So when an input comes in, it references a previous transaction. So here, for the sake of making it fit easily, I've put the entire transaction ID. By the way, this is in reverse. So if you wanted to look up this transaction, you'd need to reverse these bytes. It would be 7F305558CB, etc. That's important to note, because when you go to debug this stuff and you go look for this transaction, it doesn't exist. But if you take each byte in the opposite order, then that's what the transaction is. Again, the little Indian versus big Indian thing, I don't quite get why they chose to do it that way, especially for a hash, because it's not like it's a mathematical computation. It's essentially a string. But anyway, so this will reference this transaction ID plus previous output index. Now notice this one is not a varint. So there's a weird mixture of sometimes it's a int, sometimes it's a varint, sometimes it's all hodgepodge in here. There's ASN1 mixed in. It's all there's three or four different standards that they are hodgepodge adhering to in order to construct this thing. But the output ID and the output defines where to find the conditions. So when a verifying node sees this input, it will go look this up by index, and then in the cache, and then it will look up the output. So let's say that this over here were that output. Number of outputs is 1. So the output at index 0 is this output, which means this is the coin, and then this is the pub key hash. So it would check to see, does this public key, so here's the ASN1 ECDSA signature, and then the public key is actually right here, so I selected the wrong thing. It would check, does this public key, can it resolve to this pub key hash? And before even it checks that, this is what tells it to do that. So it reads, this amount has this script. This script requires a duplicate, equal verify, check sig, check hash. And so it will read this in, and then it will run this. But it won't do that at all. It'll just fail outright if the lock time hasn't been met.
So the outputs of this transaction where I'm paying you, the lock script doesn't get ran until a previous input is trying to spend that.
A future input is trying to spend it.
Future input is trying to spend it.
Well, it'll get validated, but there's nothing to do, right? So if you were to try to quote unquote run this script, which, I mean, technically that is correct, but I wouldn't think of it that way because it doesn't really make sense. It's just a key value pair of condition and what it's checking the condition against. It's essentially is equal to, but this condition will be validated that it's a valid condition, but it's not, and that's not necessary. I believe that is advantageous. We don't want junk to end up in the script, but it's not necessary because there's nothing to do with it right now. The only time to do something with it is when you get an input that addresses that script by its output transaction and its index. So if we had multiple outputs, so let's say the situation is reversed, we have multiple outputs. In order to spend that input, it has to go look, okay, is this output 0? Is this output 0 or is this output 1? And it'll say, okay, well, this is output 0. So I am going to look for the conditions to unlock this in output 0. Or I'm going to look for the conditions to unlock this in output 1 if the lock time has been met. And 0 means no lock time.
what's left on the transaction. We went over lock time.
So there's the lock time, there's the amount, there's the lock script that includes the address that received it, which indicates the public key that needs to validate in the signature. For the inputs, there is the previous transaction ID and the output, which together with the address and the amount form the coin. There is an ASN1 ECDSA signature, and that's in, once you get to this byte, it's in the standard ASN1 format until this byte. There's a SIGHASH type. Now, SIGHASH type is important to understand but irrelevant. SIGHASH type indicates it's actually also part of the rules for accepting this transaction. So the basic type 1 is pretty reasonable. Every signature needs to have signed this transaction with this signable transaction. So obviously you can't sign other people's signatures as part of what you're signing because everybody needs to sign everybody else's signatures. So what this says is you're going to take a version of the transaction, and that I have here, a signed transaction. This is a signable transaction. So this signable transaction has where does it have it? No, it doesn't even have to have it because it's just not there, period. This signable transaction has no signature. So you have to generate a signable transaction in order to sign it, and none of the signatures are present in the signable transaction, but otherwise all the values are the same. And every party that is signing a transaction, so every coin that goes into as an input, has to sign all of the input values and all of the output values. So they sign the signable transaction as a whole. And that is SIG type 1. It is possible at the protocol level to create very complex signature rules where one person says that they need to sign everything, another person says they only need to sign their thing, another one says that they need to sign all the inputs but they don't need to sign the outputs, another one says they need to sign the outputs but they only need to sign their own input, and various permutations of this. So there's various permutations of the signing logic at the protocol level. However, all of those problems have been solved in higher levels in a way that, to me, makes a lot more sense. So the SIGHASH type is effectively not used anymore. I don't think I've ever heard of any software that uses this because they all use some other mechanism to do the same thing. For example, now we have XPubs, and so XPubs allow you to pay somebody, actually I can't remember what the example was, but we also have WIFs. WIFs allow you to give somebody money, and you give them the private key to, you give them the blank check, they can write however much they want from what's available at that private key's address, payment address. So with that, you don't need the anonymous signature type because it's a lot easier just to give somebody your private key and say, take what you want, than it is to say, here's a signed transaction, but it doesn't say who it's to. You fill out who it's to and then submit it to the network. It just makes more sense to just give them the private key rather than keep the private key and then sign out the coin. So a lot of these things, just the use case never materialized, and where the use case did materialize, it materialized in a completely different way that is superior, which is why those ways are used and this way really isn't. And then you have the sequence. And I actually don't know what the sequence is.
Okay.
Because the sequence is not the index. But the sequence, one thing I do believe about the sequence is whereas lock time counts up, sequence counts down. But that one, the SIG hash type you need to know, because if you ever look at other implementations of the code, this implementation of the code only does payment transactions. It doesn't handle any other type of transaction. So it's very small, it's very lightweight, and it's not necessarily easy to read, but it's probably better than anything else that's out there. It is complex. It is a very strange mechanism that they chose to have such machinery. But again, this was before, because in the beginning, addresses like we have them now didn't exist. Payment addresses came later. And HD wallets came later. And all of these other features that we use today, they all came later. And so in the beginning, they were thinking about a lot of these things and they put them down in the transaction. And so transactions are really, really complicated, especially if you were to implement everything that can be done. It is monstrously complicated. But if you look at what we've actually landed on in terms of what we actually use in practice in the real world, it's a small fraction of what could be done according to the protocol. And this right here, the how to calculate signatures, does walk you through this step by step. Oh, this is where I defined varint. 1 to 9 byte integers, 0 through 252, 253, 250, yeah. uint32le, big int, opcode, pubkey hash, signature, RNS values. If you want to look at it not in the byte sequence, but just as a bulleted list, version, number of inputs, list of neutered inputs, meaning unsigned inputs, previous transaction ID, previous output index, null script, sequence number, then number of outputs, then the list of the outputs, the unit, the lock script size, which is always 25 bytes for the payment lock script transaction, the lock script itself, which is opdupe, ophash, pubkey hash, the pubkey, equal verify, check sig, and then the lock time. And then if you wanted to look at that, the hashable version, the difference is that it does include the previous lock script. And then the outputs, do the outputs define a lock script here? Yes, they do. So in the raw version, it doesn't define the lock script. In the signable version, it does include the lock script. And then in the signed version, I think I called this hashable as to not be confusing between signable and signed, because this is what you use to produce the hash that you sign, and then every input on the server side, each input is calculated separately. Each input has the set of rules that are referenced in the previous one. They get brought into this. Then it hashes according to those rules and then checks the signature according to the hash. And so for every input, it has to repeat that process independently according to the rules. And then the signed version is the one that you're ready to broadcast. If you give it to somebody, it's the same as giving them the private keys for those inputs. Well, it's not the same in that it's only signed for that particular list of outputs, but it is signed. It is a private, well, kind of a private value. It's ready to go. You put it on the block when you want to put it on the block. And then if you were looking at kind of the polymorphic view, there's the polymorphic view. So it is complex.
Um, what is a raw transaction?
The raw transaction is this right here. It's the same as, so what gets published is the signed transaction. The raw transaction has the information about the inputs and the outputs, but none of the rules, except for the lock script. It doesn't have the signature. It doesn't have the signature or the script that is used to unlock the previous input.
But it's the same as a ready to sign transaction, or
No.
what was the statement? It's the same as.
Well, it's the same. It's the same as the other ones, except there's no script included. So the inputs are neutered. That's raw transactions have neutered inputs. So if you wanted to, I think this was the rationale. I think in the beginning, nowadays we send addresses, right? So I'll send you my XPub if I want you to pay me. But in the beginning, I think that this is how they sent a payment request. I think that they gave you a transaction that had the output information filled out, but not the input information other than the amount that was requested. And so I think if you got a raw transaction, I think that was essentially a payment request, and then you would fill out multiple people. You could send a payment request to multiple people, kind of like what's happening with CoinJoin. So the raw transaction, you can send to multiple people, and then they could each independently fill it out. And then the filled out versions could be combined together into a hashable form that each could then sign. And then the signatures get added and replace I think they don't actually replace anything. They just get appended to the previous lock script, or do they replace the previous lock script? I think they replace the previous lock script is the difference. Because this has a signature block. Yes. So a raw transaction has the script nulled out. A hashable transaction has the previous lock script in the script section. The signed transaction does not have the previous lock script, but does have the new signature script.
Hashable transaction. Can you repeat that?
So the hashable transaction has the previous lock script, where the raw transaction has a null script.
Okay. And so a ready to sign transaction is like.
This is hashable. If it's hashable, it's ready to sign. Because the signature goes on the hash of the transaction.
Okay, so those are synonymous?
Yes, synonymous.
Okay.
Yeah. Hashable or ready to sign. It may have another technical name that I haven't discovered. I'm pretty sure that raw TX is called raw TX. The hashable TX or the ready to sign TX is an internal implementation detail. I have not seen it referenced outside of code. Whereas raw TX is referenced outside of code, and the signed or ready to broadcast transaction is referenced outside of code.
Okay.
But this is an internal implementation detail, so it was actually quite difficult to learn what this was because it's not referenced in documentation anywhere else. It's only referenced in code because for most of these things, there are no alternative implementations. There's one implementation and that's it. So the implementation that I copied to get this was just the C code ported to JavaScript line for line. It was, it was, if you looked at the C code and you looked at the JavaScript code, syntax is different, same logic, same comments.
Okay. I think I'm at my limit right now. Thank you for this. If we could do another one, that'd be cool. At some future point, I have a lot to digest and
This
to read
is
about, so.
this is pretty much everything I've learned over the past year.
Okay.
This is it. My cup is full. I really, everything that I have learned is pretty much summed up in the code in these. I mean, we could talk about Dash Site, but that is just an API layer and you could build it any which way you want to. It uses the Inside API, but the Inside API is admittedly abandoned by the Dash team, so
Oh, jeez.
we have to create something new for what we're doing for the wallet. But this is okay. I mean, this is what I was planning to work on this week. I need to finish up. There was something I need to finish up for Dash Wallet. I can't remember right now, but I needed to finish up something on that. Oh, it was splitting the coins out. So Dash Wallet is decidedly not fingerprint by default. It is decidedly clean transaction by default, not dirty transaction by default. So I have a little bit of implementation left for that. But yeah, Dash Wallet will not follow the tradition of Bitcoin of doing that. So Dash Wallet is going to only track down to the Millidash. It's not going to track below that. Everything below that is going to be considered exchange, basically stamp values. You know, like if you want to send a letter to somebody, you have to pay a fee. That's a stamp. And so in terms of Dash Wallet, we already have the concept of dust, which is money that's so small you can't spend it. And Dash Wallet has the idea that money that is not useful is just stamp values. And so you just basically pay it forward. You pay your fractional pennies forward to the next person for them to pay their fees with.
Cool. Well, my wife is home. I gotta head out for now. Thank you for this, man, once again.
You are welcome.
Cool. All right, man. Well, I'll see you later.
Okay, bye.
Bye.
Pew. What's up, you crazy people? Why didn't you ask any questions? My brain hurts. Oh, man.
Door.
That's the door, buddy. Looking forward to that.
Door.
Yep, it's the door.
Door.
Adios.